Good morning, everyone. This is Mrs. Rondo. We're going to be looking at an introductory lesson to transformations. Our essential question, how do we perform and describe transformations? We have two learning goals we're working on today. I can create the image of a figure given a rule and the pre-image, and then I can explain why a transformation or a sequence of transformations is rigid or non-rigid. So today we won't be doing the sequence of transformations. We're just going to look at one transformation at a time, and I'll explain all those fabulous vocabulary words in just a moment. Also today for our notes, you may want to print the notes. That would probably be the best course of action. So you could print them from Google Classroom, or the next best would be to do them in the Google Doc. I would definitely not suggest you writing these out by hand because there's graphs and stuff, but I do leave that up to you. Again, my suggestion is to print them or use the Google Doc. Here we go. So starting off at the top, transformation basics. A transformation is a function that changes a figure's position, shape, and or size. So something I would like to add in here about what transformations are is our clarification of function. This means what we sometimes call a rule, or sometimes we're going to call it an equation. Okay, so a function meaning we start with an input, we start with something, do something to it, and then get an output. So the function is the method of how we get from the input to the output. All right, so again, sometimes we call that a rule or an equation. Then we have pre-image. This is the original figure before we've done a transformation. So pre meaning before. And then we have image. This is the changed figure, or sometimes you'll hear me call this the copy. So the image is the copy of the figure. Then we have properties of rigid motion. So one of our goals is to be able to explain why a transformation is rigid motion or non-rigid. And so we need to know what rigid motion is. So rigid motion basically means that we preserve distance. And I'm going to find my pen. Where'd it go, honey? There it is. And so I'm going to star this one. Super important that we preserve distance. And I would point out here as well that you should be jotting this down. Keeps the same distances. And then this next one, also super important, preserves angle measure, meaning it keeps the same angle measure. So an angle in a figure that starts off as 30 degrees, in the answer, it will still be 30 degrees. And then the last one, less important, not less important, but we're not going to talk about it nearly to the degree, and that is preserves collinearity. That's how you say that word, collinearity. It means points that are on the same line will remain on the same line even after you've done some kind of transformation. So we're not going to talk nearly as much about that one. It is still true. It is part of the properties of rigid motion, but the two that we're going to constantly cite is that we have the same distance and the same angle measure. All right, so we're going to start off by actually doing a transformation. So transform triangle ABC according to the rule, then describe the transformation. So this information right here, this is our rule. So it tells us that we are starting with XY. So here's whatever our ordered pair is. And this part is what we are going to do to it. So we're going to take the X value and we're going to subtract 4. We're going to take the Y value and we're going to subtract 3. So before we can do any of that, whoopsie, let's bring that back. Before we can do any of that, I'm going to just have us jot down the ordered pairs. So point A is at 0, 4. Point B is at, 3, 0, over 3, up 0. And point C is at 0, 0. So if I go through and do this one at a time, I'm going to take my ordered pair for point A, and I'm going to just plug in the numbers, my X and my Y, so 0 and 4, into the rule. So I'm going to say 0 minus 4, that's coming right here from the rule, matchy matchy. And then I'm going to do 4 minus 3, and that's my second ordered pair second ordered pair, excuse me, second value in my ordered pair, putting that into the second part of my rule. Okay. So when I do all that, then I'm going to simplify, and that means my new ordered pair is going to be -4. 0 minus 4 is -4. 4 minus 3 is 1. And then for any point that we have moved, we're going to rename it. So it's going to keep the A, but we're going to call it A prime. And it's just a little apostrophe, and we say prime. And it just means it's the copy of A. So we took A and we moved it somewhere else. So it lines up, or it matches up with A. It's just in a new location. All right, so then we're going to do the same thing with B. So I'm going to plug in 3 for X and 0 for Y. And I'm going to get B prime is at -1, -3. And then that was doing the math, 3 minus 4 and 0 minus 3. Okay. And here we go. We have C. I'm going to plug in my ordered pair 0, 0. So I have 0 minus 4 and 0 minus 3. And I get C prime is at -4, -3. All right, so my A prime, B prime, C prime, those represent the points of my transformed triangle. So the triangle ABC, I'm going to move it to those new ordered pairs. So here goes, -4, 1. This is going to be A prime. I don't know why I put a minus there. I'm sorry. A prime. So that's my first transformed point. There we go. And then I'm going to do the next one, -1, -3. That would be B prime. And then -4, -3 would put me down here at C prime. And then, of course, I would connect the dots. Hopefully, we'll see how good I can do at connecting the dots. Try that one more time. And that gives us our new location. All right, so the first part of our directions here were to transform the triangle, which we did. We moved it. We finished the transformation. And then describe it. So what we're looking for in terms of the description is what happened to the triangle ABC. So the original triangle is no longer in the same location. So I would say triangle ABC has changed locations. That's the first thing. It didn't change size. It didn't change shape. All it did was move. We just kind of moved it over. So it's changed locations. And then the other comment we would make is about whether or not this is rigid motion. So the key for rigid motion is that all the lengths, so the distances for your sides, all the lengths and all the angles stay the same. Or another way of looking at it, and actually I'm going to go back to our rigid motion here. Another way of looking at rigid motion is only location changes. Okay, so only the location changes. We do not change the size or the shape. If you change the size or the shape, that's a different kind of transformation. That's called a non-rigid motion. Okay, so rigid motion is only going to change the location. So this one would be rigid motion. All right, let's go on to the next one. Transform triangle RST according to the rule, then describe the transformation. So one more time, we're going to go through and list our ordered pairs. R is at -4, 3, I believe. S is at -1, 3. And T is at -4, 1. -4, 1. Okay. Yep. Great. Then my rule, I'm going to apply my rule. So I'm going to go through, and this time the rule is a little bit different. We're not adding or subtracting this time. We just have a negative in front of the y. So the x's are not going to change. I'm just going to simply rewrite them. So I would apply the rule. I plug in -4 for my x, but for the y, it says do -y. So I'm going to do negative, and then the y value I have is 3. So when I simplify that, I would get r prime is at -4, -3. Let's try it again. So this time the x value, I'm just copying it. The y value, it says do negative, and then I plug in the y value, which is 3. And I get s prime at -1, -3. And then the last one, again, the x value stays the same. Then I do negative, and then the y value would be plugged in. I get a 1. So t prime, sorry, just wanted that to be a smidge neater. T prime is at -4, -1. Okay, so then we're going to go put those points on the graph so we can actually do the transformation. So r would be at -4, -3, r prime, excuse me, r prime. Great. Then s prime is at -1, -3, s prime. And then t prime is at -4, -1. This would be t prime. I'm going to move my r prime a little bit here just to make this a little more clear. Fantastic. Okay. And there's my transformation. So I'm going to, of course, connect the dots. And then we're going to talk about describing this. So one more time, when I look at the result, what happened to RST is it moved. It's not in the exact same location, but also it's kind of been flipped over. What we will later call that a reflection. For now, you can do that if you would like. I'm going to say triangle RST has flipped locations. Again, later we'll call it a reflection, and that's fine. For now, it's flipped locations. It's moved. And did it change size or shape? No, it's still the same size. It's still the same shape. So this would be a rigid motion. So as long as the size and shape are the same and all we did was move it, it's going to be rigid motion. Okay. The last one of this type, this type of example, we're going to transform triangle JKL. Here we go. J is at -1, comma 2. These ordered pairs correctly here. And then K is at, looks like 2, 2. Aha, 2, 2. Okay, anyways. Next one, L is at 2, -4. All right, so we're going to follow the rule, which this time we have 2 times x. So I'm going to do 2 times x, comma, and then the y value is going to stay the same. And then I will fix that up, and I get j prime at -2, 2. Then for my next one, for k, again, the x value has 2 times the x value, y value stays the same. K prime is at 4, 2. And finally, the L, 2 times the x value, y value stays the same. L prime is at 4, -4. All right, so let's see how that looks on our graph. Going over to J prime is at -2, 2. Then I have K prime is at, sorry to make that prime a little clearer. I don't think I made it any clearer. Try one more time. J prime. There we go. Okay, and K prime is at 4, 2. 2, K prime. And then L prime is at 4, -4. So 4, -4. All right, and then we would connect those dots. Add that a little bit. Come on, honey. Oh, wow, that is not a straight line. I'm so sorry. Had a rough start. Let's try that one more time. All right, so as I'm connecting, you guys should be looking at this new triangle, and hopefully we recognize there's something different about it. It's not the best. Let's see if I can draw that one more time. So there is something different about this new triangle. The new triangle, or the image, the copy that we have made after our transformation, is a bit different than the original. So we are going to say triangle, and we're looking for JKL. So the original triangle JKL, what happened to it? Well, it kind of got stretched out. So I'm going to say JKL is stretched. And I might even comment that it's been stretched. It's kind of been pulled, like as if I grabbed the right and the left side and kind of pulled it. It didn't change how tall it is. It's still the same height up and down. It's just been stretched. So I might say stretched horizontally, which means left to right. And then in terms of rigid motion, we're looking for rigid motion means the only thing that changed was location. We did not change size or shape. So is that true for this figure? Did we change the size or shape? On this one, yes, we did change the shape. It's still a triangle, but it's a different shape triangle, and it's kind of bigger. So this one would be non-rigid. This is a non-rigid motion transformation because it changed the size and shape. It was not a simple moving. So rigid motion is just moving. Non-rigid motion is you're changing size or shape. So there we go. Let's look at the next type of example we're going to see. Write the rule that carries the pre-image onto the image, then determine whether the transformation is rigid or non-rigid. Okay, so this time we're given the picture of the pre-image and image. We're given the ordered pairs, and we are asked to create the rule. So to do that, we're going to be looking for patterns. So on this one, if we look at the original and compare it to the copy, so the pre-image compared to the image, if you look at all of the actual numbers, ignore the signs for a minute, hopefully you notice they are the same. 4, 4, 4, 4. 2, 4, 2, 4. 4, 1, 4, 1. Okay, and so it won't always be this, but this one happens to have that particular pattern that I noticed all those numbers are the same. So what's been changed? So you can do that one step at a time. If I look at D to D prime, my X value was originally -4, and in the answer, it's +4. So what happened? The sign changed, or it's the opposite. The way that we represent that mathematically, we're going to say XY, the original, is changed by making the X value the opposite. Okay, so we can always test it out. So I could try -4, and then if I follow that rule, that means I would do -4. And then when I go to the end result of that, I would get -4. Negative times a negative is +4. All right, so let's try it with the Y's. And let's see what we get for the Y's. So with the Y's, I start with a 4, and then I end up with -4. So I go 4 to -4. So the sign, once again, is changing. The way that we change a sign is with a negative. So I would say -Y. And again, I can test it out. So I'm going to go, I start with 4. Then this tells me, right here, tells me to do the negative version. I actually should have my parenthesis there. It's going to bother me that it's not there. Let's put that in. Okay, so it looks like this is going to be our rule, but we're going to finish testing it out and see if it works. So I'm going to I have 4 for my ordered pair, and then I plug that in for the Y. It tells me to do -4. And so -4 gives me -4. So it works. And I could test it for all the additional points. If you look at the next one for E, that one's really easy to see that I took the X and Y were 2 and 4, and I made them both negative. So you can see it works for that one as well. But again, you could test it for all of them and see that it works. So I'm going to get rid of, I'm going to get rid of all this. Sorry. Bye. Can always rewind it and get that part again. Okay, so that is our rule. We're supposed to write the rule that carries the pre-image onto the image. So if we followed that rule, triangle DEF would become D prime, E prime, F prime. Then determine whether the transformation is rigid or non-rigid. So did we change the size or shape? Well, the size, it looks like it's the same size triangle, but we want to be sure. So I'm going to actually go through and compare every single side just to be sure. So I would say DF. How long is it from D to F? Well, if I count that, and actually I'm going to do this in color. I lied to you guys. I'm sorry. Here we go. Apparently I didn't warn you. Go get some colors. Okay, we're going to go. We'll go blue. Okay, so D. Wow, it's really bad. Try that one more time. Okay, D to F. I get 3 units. So I'm going to say D to F is 3. Then I'm going to compare that D prime to F prime, which is over here. And I get 3. Which is good because we expect them to be the same. Or if it's rigid motion, we expect them to be the same. They look like they're the same, so we'll probably be fine. Okay, then I'm going to change colors. Now I'm going to go to, let's do orange. And I'm going to go up here. Come on, honey. Can't find my little marker. There it is. It's hard to see when I move it. Okay, so I have D to E. I'm going to go D to E. And if I count that across 1, 2, 3, 4, 5, 6, looks like it's 6 across. And then I'm going to check D prime to E prime. Let's check that one. Looks like that one is also 6. And then I'm actually going to go back to my purple, which you could just use your regular writing utensil, or you could actually use purple. And then I'm going to check E to F. So I'm going to go E to F. And when I go to do this one, I run into a slight problem. My slight problem is that this is at an angle, so I can't count how many boxes. But this happens to be a right triangle because I have a horizontal and vertical legs here, my D, F, and D, E. So I can quickly do some Pythagorean theorem and figure this out. So for EF, this would be, if I take my one side, which would be, remember Pythagorean theorem is, actually we'll do it over here for us, is a squared plus b squared equals c squared. And actually, without even doing Pythagorean theorem, you should be able to tell me that these two sides are going to be the same, because when I look at my numbers for the sides for both triangles, they are the same. So I really only have to do this once just to prove it. 3 squared plus 6 squared equals c squared. 3 squared, I would get 9. 6 squared, I get 36 equals c squared. And sorry, I lost my train of thought for a quick second. Then I get 45 equals c squared. And then to get c by itself, I would square root. And I get c is the square root of 45, which we could reduce. I'm not super worried about it because I can go back to my problem and say, hey, e to f, or what I had labeled c, is square root 45. And then if we compare e prime to f prime, we're going to be using that same math equation, and we can say, oh, e prime to f prime also happens to be square root 45. So that would be our way of proving, in this case, that, and actually I'm already on this color perfect, that this is rigid motion. because we keep the same distances. And we didn't measure the angles. If we were in class with protractors, we would probably measure the angles as well. But for now, we'll just look at distance. Okay, one more of those and then we are done. Let's wrap it up quickly. Same kind of deal. Write the rule. This one, when I go and look at my numbers, they are not the same at all. So I'm going to go one step at a time and compare my x value to my x value. I had -3. How do I get to -2? And then if I do that same thing, comparing x's first, 2 to 3, that one looks really easy to me. Oh, I just added 1. 2 plus 1 is 3. Is that true for this one? Let's check it out. -3 plus 1. Oh yeah, it's -2. Excuse me, looks like it works. So I can start writing my rule. X, y is going to become x plus 1 because I took my x value and I added the 1 to get the new answer. Okay, oopsie, forward. I'm going to get rid of some of my crazy markings here. Great. And now let's look at the y's. All right, so y values, I start at 4 and I end at 2. That looks like I'm going to subtract 2. Let's see if it works. Then I have 4 that goes to 2. That's also subtract 2. And I have 0 that goes to -2. That would also be 0 minus 2 is -2. Looks like it works. So I would write y minus 2. So there's my rule. Get rid of all this craziness. Great. And then I need to go through and actually prove it on my picture. So this time I'm actually going to start with my purple, what I was using for my regular utensil, and I'm going to check S to T and S prime to T prime, because that one I can easily count. There we go. And if I do that, I have ST equals 1, 2, 3, 4, 5, and S prime to T prime also equals 5. Fantastic. Then I'm going to switch colors and go to blue. And I'm going to look at, let's do, well, I want to do SU because I already started to highlight it. Okay, so I'm going to do SU and S prime U prime. I'm looking for those to be the same. So I need to make sure that their distance is the same. Well, I can do that by doing full-on distance formula, or I could create myself, whoopsie, a nice little right triangle right here. And this right triangle would be 4 and 1 for my lengths. So I could quickly do Pythagorean theorem. So the distance from S to U would equal a squared, which in my case is 1 squared, and then b squared, in my case, that would be 4. And so if I simplify, I get 1 plus 16. 1 squared is 1. 4 squared is 16. I get S, oops, I made a big uh-oh. And this is SU squared. A squared plus B squared equals C squared. Excuse me, I don't know what I was thinking. So I have SU is squared, or SU squared is 17. To figure out SU, my last step here would be to square root both sides. And I get the actual distance for SU is square root 17. And I'm not worried about approximating it because we're just trying to see if they match. All right, for the other one, then S prime to U prime, again, I could create that little triangle. And when I do, I see the same numbers. So S prime U prime squared is equal, this is my A squared plus B squared. This is representing my C squared. That's where I got carried away last time. I forgot about saying C squared. Okay, so my A squared and B squared again are 1, the A squared, 1 squared, B squared is 4 squared. So I'm going to end up with that same answer of square root 17. I don't have to do the math all over again. I can just say, hey, look, the numbers, oopsie, ended up being the same. Okay, so I'm going to switch to orange for my last one. We're going to wrap it up here. So I have U to T or T to U. Let's do T to U. And I want to check those. For these, I'm going to actually do distance formula. You could, again, create a right triangle, but I want us to go back and practice distance formula. So I'm going to do that, and you guys can copy along as you go. So I'm going to go T to U, and so I'm going to start here on my pre-image. I'm going to call the T's the 1s and the U's the 2s for my ordered pairs. So I'm going to say TU is the square root of, this is our distance formula. I take the x values, I'm going to subtract them. So the second x value, which would be -2, minus the first. That's for my 2's and my 1's over there. Then I do plus, then I'm going to do my y values, the second y value minus the first. Then I'm going to simplify that. And I get square root of -2 minus 2 is -4. 0 minus 4 is -4. Then if I square those, I get 16 plus 16, or I end up with TU equals square root 32. Like I said, for our purposes here, we're not super worried about it being simplified. We're just trying to match it up. Okay, so now I'm going to test out T prime U prime. I'm hoping that it equals square root 32, and then I can say this is rigid motion. So I'm going to do my big distance formula, and I'm going to come back and I'm going to label this again 1 and 2. So I do the x value from order pair 2, which is -1, minus the x value from order pair 1. Then the y value from order pair 2 minus the y value from order pair 1. Then I'm going to simplify. So T prime U prime, and we get square root of -4 squared plus -4 squared. Right there, you should notice that that matches what we had before, but I will still show just a little bit more work here and say, hey, this is the square root of 16 plus 16, or square root 32. So they match. So I'm going to go through and just point out that they all match up. So I have, this would be rigid motion, because we kept the same distances and we proved that they were the same distances for every single side of the triangle. All right, that's it for notes. You guys can check out the homework on Google Classroom. Thanks. Have a great day.